Section 9 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Kieran Metz. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 9. Pathological Colors. Appendix 101. We are now sufficiently acquainted with the physiological colors to distinguish them from the pathological. We know what appearances belong to the eye in a healthy state and are necessary to enable the organ to exert its complete vitality and activity. 102. Morbid phenomena indicate in like manner the existence of organic and physical laws. For if a living being deviates from those rules with reference to which it is constructed, it still seeks to agree with the general vitality of nature in conformity with general laws, and throughout its whole course still proves the constancy of those principles on which the universe has existed, and by which it is held together. 103. We will here first advert to a very remarkable state in which the vision of many persons is found to be. As it presents a deviation from the ordinary mode of seeing colors, it might be fairly classed under morbid impressions, but as it is consistent in itself, as it often occurs, may extend to several members of a family, and probably does not admit of cure, we may consider it as bordering only on the nosological cases, and therefore place it first. 104. I was acquainted with two individuals not more than 20 years of age who were thus affected. Both had bluish-gray eyes, an acute sight for near and distant objects, by daylight and candlelight, and their mode of seeing colors was in the main quite similar. 105. They agreed with the rest of the world in denominating white, black, and gray in the usual manner. Both saw white untinged with any hue. One saw a somewhat brownish appearance in black, and in gray a somewhat reddish tinge. In general, they appeared to have a very delicate perception of the gradations of light and dark. 106. They appeared to see yellow, and yellow-red like others. In the last case, they said they saw the yellow passing as it were over the red as if glazed. Some thickly ground carmine which had dried in a saucer, they called red. 107. But now a striking difference presented itself. If the carmine was passed thinly over the white saucer, they would compare the light color thus produced to the color of the sky, and call it blue. If a rose was shown them beside it, they would, in like manner, call it blue. And in all the trials which were made, it appeared that they could not distinguish light blue from rose color. They confounded rose color, blue, and violet on all occasions. These colors only appeared to them to be distinguished from each other by delicate shades of lighter, darker, intenser, or fainter appearance. 108. Again, they could not distinguish green from dark orange, nor, more especially, from a red-brown. 109. If anyone, accidentally conversing with these individuals, happened to question them about surrounding objects, their answers occasioned the greatest perplexity, and the interrogator began to fancy his own wits were out of order. With some method we may, however, approach to a nearer knowledge of the law of this deviation from the general law. 110. These persons, as may be gathered from what has been stated, saw fewer colors than other people. Hence arose the confusion of different colors. They called the sky rose color and the rose blue, or vice versa. The question now is, did they see both blue or both rose color? Did they see green-orange or orange-green? 111. This singular enigma appears to solve itself if we assume that they saw no blue, but instead of it a light pure red, a rose color. We can comprehend what would be the result of this by means of the chromatic diagram. 112. If we take away blue from the chromatic circle, we shall miss violet and green as well. Pure red occupies the place of blue and violet, and in again mixing with yellow, the red produces orange where green should be. 113. Professing to be satisfied with this mode of explanation, we have named this remarkable deviation from ordinary vision acyanoblepsia. We have prepared some colored figures for its further elucidation, and in explaining these we shall add some further details. Among the examples will be found a landscape colored in the mode in which the individuals alluded to appear to see nature, the sky rose color, and all that should be green, varying from yellow to brown-red, nearly as foliage appears to us in autumn. 114. We now proceed to speak of morbid and other extraordinary affections of the retina, by which the eye may be susceptible of an appearance of light without external light, reserving for a future occasion the consideration of galvanic light. 115. If the eye receives a blow, sparks seem to spread from it. In some states of body, again, when the blood is heated and the system much excited, if the eye is pressed first gently and then more and more strongly, a dazzling and intolerable light may be excited. 116. If those who have been recently couched experience pain and heat in the eye, they frequently see fiery flashes and sparks. These symptoms last sometimes for a week or fortnight, or till the pain and heat diminish. 117. A person suffering from earache saw sparks and balls of light in the eye during each attack as long as the pain lasted. 118. Persons suffering from worms often experience extraordinary appearances in the eye, sometimes sparks of fire, sometimes specters of light, sometimes frightful figures, which they cannot by an effort of the will cease to see. Sometimes these appearances are double. 119. Hypochondriacs frequently see dark objects such as threads, hairs, spiders, flies, wasps. These appearances also exhibit themselves in the incipient hard cataract. Many see semi-transparent small tubes, forms like wings of insects, bubbles of water of various sizes which fall slowly down if the eye is raised. Sometimes these congregate together so as to resemble the spawn of frogs. Sometimes they appear as complete spheres, sometimes in the form of lenses. 120. As light appeared in the former instances without external light, so also these images appear without corresponding external objects. The images are sometimes transient, sometimes they last during the patient's life. Color, again, frequently accompanies these impressions. For hypochondriacs often see yellow-red stripes in the eye. These are generally more vivid and numerous in the morning or when lasting. 121. We have before seen that the impression of any object may remain for a time in the eye. This we have found to be a physiological phenomenon. The excessive duration of such an impression, on the other hand, may be considered as morbid. 122. The weaker the organ, the longer the impression of the image lasts. The retina does not so soon recover itself, and the effect may be considered as a kind of paralysis. 123. This is not to be wondered at in the case of dazzling lights. If anyone looks at the sun, he may retain the image in his eyes for several days. Boyle relates an instance of 10 years. 124. The same takes place in a certain degree with regard to objects that are not dazzling. Bush relates of himself that the image of an engraving, complete in all its parts, was impressed on his eye for 17 minutes. 125. A person inclined to fullness of blood retained the image of a bright red calico with white spots many minutes in the eye, and saw it float before everything like a veil. It only disappeared by rubbing the eye for some time. 126. Schurfer observes that the red color, which is the consequence of a powerful impression of light, may last for some hours. 127. As we can produce an appearance of light on the retina by pressure on the eyeball, so by a gentle pressure a red color appears, thus corresponding with the afterimage of an impression of light. 128. Many sick persons, on awaking, see everything in the color of the morning sky, as if through a red veil. So, if in the evening they doze and wake again, the same appearance presents itself. It remains for some minutes, and always disappears if the eye is rubbed a little. Red stars and balls sometimes accompany the impression. This state may last for a considerable time. 129. The Aeronauts, particularly Zambacari and his companions, relate that they saw the moon blood red at the highest elevation. As they had ascended above the vapors of the earth, through which we see the moon and sun naturally of such a color, it may be suspected that this appearance may be classed with the pathological colors. The senses, namely, may be so influenced by an unusual state that the whole nervous system, and particularly the retina, may sink into a kind of inertness and inexcitability. Hence, it is not impossible that the moon might act as a very subdued light, and thus produce the impression of the red color. The sun even appeared blood red to the aeronauts of Hamburg. If those who are at some elevation in a balloon scarcely hear each other speak, may not this, too, be attributed to the inexcitable state of the nerves as well as to the thinness of the air? 130. Objects are often seen by sick persons in variegated colors. Boyle relates an instance of a lady who, after a fall by which an eye was bruised, saw all objects, but especially white objects, glittering in colors, even to an intolerable degree. 131. Physicians give the name of crypsia to an affection of the sight occurring in typhoid maladies. In these cases, the patients state that they see the boundaries of objects colored where light and dark meet. A change probably takes place in the humors of the eye, through which their achromatism is affected. 132. In cases of milky cataract, a very turbid crystalline lens causes the patient to see a red light. In a case of this kind, which was treated by the application of electricity, the red light changed by degrees to yellow and at last to white when the patient again began to distinguish objects. These changes of themselves warranted the conclusion that the turbid state of the lens was gradually approaching the transparent state. We shall be enabled easily to trace this effect to its source as soon as we become better acquainted with the physical colors. 133. If again it may be assumed that a jaundiced patient sees through an actually yellow-colored humor, we are at once referred to the department of chemical colors, and it is thus evident that we can only thoroughly investigate the chapter of pathological colors when we have made ourselves acquainted with the whole range of the remaining phenomena. What has been adduced may therefore suffice for the present, till we resume the further consideration of this portion of our subject. 134. In conclusion, we may, however, at once advert to some peculiar states or dispositions of the organ. There are painters who, instead of rendering the colors of nature, diffuse a general tone, a warm or cold hue, over the picture. In some, again, a predilection for certain colors displays itself, in others a want of feeling for harmony. 135. Lastly, it is also worthy of remark that savage nations, uneducated people, and children have a great predilection for vivid colors, that animals are excited to rage by certain colors, that people of refinement avoid vivid colors in their dress and the objects that are about them, and seem inclined to banish them altogether from their presence. End of Section 9. Recording by Kieran Metz.
Section 10 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Karen Almeida, Bern, Switzerland. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 10. Part 2. Physical Colors. 136. We give this designation to colors which are produced by certain material mediums. These mediums, however, have no color themselves, and may be either transparent, semi-transparent, yet transmitting light, or altogether opaque. The colors in question are thus produced in the eye through such external given causes, or are merely reflected to the eye when by whatever means they are already produced without us. Although we thus ascribe to them a certain objective character, their distinctive quality still consists in their being transient and not to be arrested. 137. They are called by former investigators colores apparentes, fluxi, fugitivi, fantastici, falsi, variantes. They are also called speziosi and emphatici on account of their striking splendor. They are immediately connected with the physiological colors and appear to have but little more reality. For, while in a production of the physiological colors the eye itself was chiefly efficient, and we could only perceive the phenomena thus evoked within ourselves, but not without us, we have now to consider the fact that colors are produced in the eye by means of colorless objects, that we thus too have a colorless surface before us which is acted upon as the retina itself is, and that we can perceive the appearance produced upon it without us. In such a process, however, every observation will convince us that we have to do with colors in a progressive and mutable, but not in a final or complete state. 138. Hence, in directing our attention to these physical colors, we find it quite possible to place an objective phenomenon beside a subjective one, and often by means of the union of the two successfully to penetrate farther into the nature of the appearance. 139. Thus in the observations by which we become acquainted with the physical colors, the eye is not to be considered as acting alone, nor is the light ever to be considered in immediate relation with the eye, but we direct our attention especially to the various effects produced by mediums, those mediums being themselves colorless. 140. Light under these circumstances may be affected by three conditions. First, when it flashes back from the surface of a medium, in considering which catoptrical experiments invite our attention. Secondly, when it passes by the edge of a medium, the phenomena thus produced were formerly called perioptical. We prefer the term paroptical. Thirdly, when it passes through either a merely light-transmitting or an actually transparent body, thus constituting a class of appearances on which dioptrical experiments are founded. We have called a fourth class of physical colors epoptical, as the phenomena exhibit themselves on the colorless surface of bodies under various conditions, without previous or actual dye. 141. In examining these categories with reference to our three leading divisions, according to which we consider the phenomena of colors in a physiological, physical, or chemical view, we find that the catoptrical colors are closely connected with the physiological. The paroptical are already somewhat more distinct and independent. The dioptrical exhibit themselves as entirely and strictly physical. And as having a decidedly objective character, the epoptical, although still only apparent, may be considered as the transition to the chemical colors. 142. If we were desirous of prosecuting our investigation strictly in the order of nature, we ought to proceed according to the classification which has just been made. But in didactic treatises, it is not of so much consequence to connect as to duly distinguish the various divisions of a subject, in order that at last, when every single class and case has been presented to the mind, the whole may be embraced in one comprehensive view. We therefore turn our attention forthwith to the dioptrical class, in order at once to give the reader the full impression of the physical colors and to exhibit their characteristics the more strikingly. Section 9. Dioptrical colors. 143. Colors are called dioptrical when a colorless medium is necessary to produce them. The medium must be such that light and darkness can act through it either on the eye or on opposite surfaces. It is thus required that the medium should be transparent, or at least capable, to a certain degree, of transmitting light. 144. According to these conditions, we divide the dioptrical phenomena into two classes, placing in the first those which are produced by means of imperfectly transparent, yet light-transmitting mediums, and in the second, such as are exhibited when the medium is in the highest degree transparent. End of section 10. Section 11 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Karen Almeida, Bern, Switzerland. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 11. Section 10. Dioptrical Colors of the First Class. 145. Space, if we assume it to be empty, would have the quality of absolute transparency to our vision. If this space is filled so that the eye cannot perceive that it is so, there exists a more or less material transparent medium, which may be of the nature of air and gas, may be fluid or even solid. 146. The pure and light-transmitting semi-transparent medium is only in the accumulated form of the transparent medium. It may, therefore, be presented to us in three modes. 147. The extreme degree of this accumulation is white, the simplest, brightest, first opaque occupation of space. 148. Transparency itself, empirically considered, is already the first degree of the opposite state. The intermediate degrees from this point to opaque white are infinite. 149. At whatever point short of opacity we arrest the thickening medium, it exhibits simple and remarkable phenomena when placed in relation with light and darkness. 150. The highest degree of light, such as that of the sun, of phosphorus burning in oxygen, is dazzling and colorless. So the light of the fixed stars is for the most part colorless. The light, however, seen through a medium, but very slightly thickened, appears to us yellow. If the density of such a medium be increased, or if its volume become greater, we shall see the light gradually assume a yellow-red hue, which at last deepens to a ruby color. 151. If on the other hand darkness is seen through a semi-transparent medium, which is itself illumined by a light striking on it, a blue color appears. This becomes lighter and paler as the density of the medium is increased, but on the contrary appears darker and deeper the more transparent the medium becomes. In the least degree of dimness, short of absolute transparence, always supposing a perfectly colorless medium, this deep blue approaches the most beautiful violet. 152. If this effect takes place in the eye as here described, and may thus be pronounced to be subjective, it remains further to convince ourselves of this by objective phenomena. For a light thus mitigated and subdued illumines all objects in like manner with a yellow, yellow-red, or red hue. And, although the effect of darkness through the non-transparent medium does not exhibit itself so powerfully, yet the blue sky displays itself in the camera obscura very distinctly on white paper, as well as every other material color. 153. In examining the cases in which this important leading phenomenon appears, we naturally mention the atmospheric colors first. Most of these may be here introduced in order. 154. The sun, seen through a certain degree of vapor, appears with a yellow disk. The center is often dazzlingly yellow when the edges are already red. The orb, seen through a thick yellow mist, appears ruby red, as was the case in 1794, even in the north. The same appearance is still more decided, owing to the state of the atmosphere when the scirocco prevails in southern climates. The clouds generally surrounding the sun in the latter case are of the same color, which is reflected again on all objects. The red hues of morning and evening are owing to the same cause. The sun is announced by a red light in shining through a greater mass of vapors. The higher he rises, the yellower and brighter the light becomes. 155. If the darkness of infinite space is seen through atmospheric vapors illumined by the daylight, the blue color appears. On high mountains the sky appears by day intensely blue, owing to the few thin vapors that float before the endless dark space. As soon as we descend in the valleys, the blue becomes lighter, till at last, in certain regions, and in consequence of increasing vapors, it altogether changes to a very pale blue. 156. The mountains, in like manner, appear to us blue, for as we see them at so great a distance that we no longer distinguish the local tints, and as no light reflected from their surface acts on our vision, they are equivalent to mere dark objects which, owing to the interposed vapors, appear blue. 157. So we find the shadowed parts of nearer objects are blue when the air is charged with thin vapors. 158. The snow mountains, on the other hand, at a great distance, still appear white, or approaching to a yellowish hue, because they act on our eyes as brightness seen through atmospheric vapor. 159. The blue appearance at the lower part of the flame of a candle belongs to the same class of phenomena. If the flame be held before a white ground, no blue will be seen, but this color will immediately appear if the flame is opposed to a black ground. This phenomena may be exhibited most strikingly with a spoonful of lighted spirits of wine. We may thus consider the lower part of the flame as equivalent to the vapor which, although infinitely thin, is still apparent before the dark surface. It is so thin that one may easily see to read through it. On the other hand, the point of the flame which conceals objects from our sight is to be considered a self-illuminating body. 160. Lastly, smoke is also to be considered as a semi-transparent medium, which appears to us yellow or reddish before a light ground, but blue before a dark one. 161. If we now turn our attention to fluid mediums, we find that water, deprived in a very slight degree of its transparency, produces the same effects. 162. The infusion of the lignum nephriticum, Guilandina lineae, which formerly excited so much attention, is only a semi-transparent liquor, which in dark wooden cups must appear blue, but held towards the sun in a transparent glass must exhibit a yellow appearance. 163. A drop of scented water, of spirit varnish, of several metallic solutions, may be employed to give various degrees of opacity to water for such experiments. Spirit of soap perhaps answers best. 164. The bottom of the sea appears to divers of a red color in bright sunshine. In this case the water, owing to its depth, acts as a semi-transparent medium. Under these circumstances, they find the shadows green, which is the complemental color. 165. Among solid mediums, the opal attracts our attention first. Its colors are at least partly to be explained by the circumstance that it is, in fact, a semi-transparent medium, through which sometimes light, sometimes dark, substrata are visible. 166. For these experiments, however, the opal glass, vitrum astroides girasol, is the most desirable material. It is prepared in various ways, and its semi-opacity is produced by metallic oxides. The same effect is produced also by melting pulverized and calcined bones together with the glass, on which account it is also known by the name of beinglas. But prepared in this mode, it easily becomes too opaque. 167. This glass may be adapted for experiments in various ways. It may either be made in a very slight degree non-transparent, in which case the light seen through various layers placed one upon the other may be deepened from the lightest yellow to the deepest red, or, if made originally more opaque, it may be employed in thinner or thicker laminae. The experiments may be successfully made in both ways. In order, however, to see the bright blue color, the glass should neither be too opaque nor too thick, for, as it is quite natural that darkness must act weakly through the semi-transparent medium, so this medium, if too thick, soon approaches whiteness. 168. Panes of glass throw a yellow light on objects through those parts where they happen to be semi-opaque, and these same parts appear blue if we look at a dark object through them. 169. Smoked glass may be also mentioned here, and is, in like manner, to be considered as a semi-opaque medium. It exhibits the sun more or less ruby-colored, and, although this appearance may be attributed to the black-brown color of the soot, we may still convince ourselves that a semi-transparent medium here acts as if we hold such a glass moderately smoked and lit by the sun on the unsmoked side before a dark object, for we shall then perceive a bluish appearance. 170. A striking experiment may be made in a dark room with sheets of parchment. If we fasten a piece of parchment before the opening in the window shutter when the sun shines, it will appear nearly white. By adding a second, a yellowish color appears, which still increases as more leaves are added, till at last it changes to red. 171. A similar effect, owing to the state of the crystalline lens in milky cataract, has been already adverted to. 172. Having now, in tracing these phenomena, arrived at the effect of a degree of opacity scarcely capable of transmitting light, we may here mention a singular appearance which was owing to a momentary state of this kind. A portrait of a celebrated theologian had been painted some years before the circumstance to which we allude, by an artist who was known to have considerable skill in the management of his materials. The very reverend individual was represented in a rich velvet dress, which was not a little admired, and which attracted the eye of the spectator almost more than the face. The picture, however, from the effect of the smoke of lamps and dust, had lost much of its original vivacity. It was therefore placed in the hands of a painter who was to clean it and give it a fresh coat of varnish. This person began his operations by carefully washing the picture with a sponge. No sooner, however, had he gone over the surface once or twice and wiped away the first dirt, than to his amazement the black velvet dress changed suddenly to a light blue plush, which gave the ecclesiastic a very secular, though somewhat old-fashioned, appearance. The painter did not venture to go on with his washing. He could not comprehend how a light blue should be the ground of the deepest black, still less how he could so suddenly have removed a glazing color capable of converting the one tint to the other. At all events, he was not a little disconcerted at having spoilt the picture to such an extent. Nothing to characterize the ecclesiastic remained but the richly curled round wig, which made the exchange of a faded plush for a handsome new velvet dress far from desirable. Meanwhile, the mischief appeared irreparable, and the good artist, having turned the picture to the wall, retired to rest with a mind ill at ease. But what was his joy the next morning, when, on examining the picture, he beheld the black velvet dress again in its full splendor. He could not refrain from again wetting a corner, upon which the blue color again appeared, and after a time vanished. On hearing of this phenomenon, I went at once to see the miraculous picture. A wet sponge was passed over it in my presence, and the change quickly took place. I saw a somewhat faded but decidedly light blue plush dress, the folds under the arm being indicated by some brown strokes. I explained this appearance to myself by the doctrine of the semi-opaque medium. The painter, in order to give additional depth to his black, may have passed some particular varnish over it. On being washed, this varnish imbibed some moisture and hence became semi-opaque, in consequence of which the black underneath immediately appeared blue. Perhaps those who are practically acquainted with the effect of varnishes may, through accident or contrivance, arrive at some means of exhibiting this singular appearance as an experiment to those who are fond of investigating natural phenomena. Notwithstanding many attempts, I could not myself succeed in reproducing it. 173. Having now traced the most splendid instances of atmospheric appearances, as well as other less striking yet sufficiently remarkable cases, to the leading examples of semi-transparent mediums, we have no doubt that attentive observers of nature will carry such researches further, and accustom themselves to trace and explain the various appearances which present themselves in everyday experience on the same principle. We may also hope that such investigators will provide themselves with an adequate apparatus in order to place remarkable facts before the eyes of others who may be desirous of information. 174. We venture, once for all, to call the leading appearance in question, as generally described in the foregoing pages, a primordial and elementary phenomenon, and we may here be permitted at once to state what we understand by the term. 175. The circumstances which come under our notice in ordinary observation are, for the most part, insulated cases, which, with some attention, admit of being classed under general leading facts. These again range themselves under theoretical rubrics which are more comprehensive and through which we become better acquainted with certain indispensable conditions of appearances in detail. From henceforth everything is gradually arranged under higher rules and laws, which, however, are not to be made intelligible by words and hypotheses to the understanding merely, but, at the same time, by real phenomena to the senses. We call these primordial phenomena because nothing appreciable by the senses lies beyond them. On the contrary, they are perfectly fit to be considered as a fixed point to which we first ascended, step by step, and from which we may, in like manner, descend to the commonest case of everyday experience. Such an original phenomena is that which has lately engaged our attention. We see on the one side light, brightness, on the other darkness, obscurity. We bring the semi-transparent medium between the two, and from these contrasts and this medium the colors develop themselves, contrasted, in like manner, but soon, through a reciprocal relation, directly tending again to a point of union. 176. With this conviction we look upon the mistake that has been committed in the investigation of this subject to be a very serious one, inasmuch as a secondary phenomenon has been thus placed higher in order. The primordial phenomenon has been degraded to an inferior place. Nay, the secondary phenomenon has been placed at the head. A compound effect has been treated as simple, a simple appearance as compound. Owing to this contradiction, the most capricious complication and perplexity have been introduced into physical inquiries, the effects of which are still apparent. 177. But when even such a primordial phenomenon is arrived at, the evil still is that we refuse to recognize it as such, that we still aim at something beyond, although it would become us to confess that we are arrived at the limits of experimental knowledge. Let the observer of nature suffer the primordial phenomena to remain undisturbed in its beauty. Let the philosopher admit it into his department, and he will find that important elementary facts are a worthier basis for further operations than insulated cases, opinions, and hypotheses. End of section 11.
Section 12 of Theory of Colours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Gillian Hendry. Theory of Colours by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 12. 11. Dioptrical colours of the second class. Refraction. 178. Dioptrical colours of both classes are closely connected, as will presently appear on a little examination. Those of the first class appeared through semi-transparent mediums. Those of the second class will now appear through transparent mediums. But since every substance, however transparent, may be already considered to partake of the opposite quality, as every accumulation of a medium called transparent proves, so the near affinity of the two classes is sufficiently manifest. 179. We will, however, first consider transparent mediums abstractly as such, as entirely free from any degree of opacity, and direct our whole attention to a phenomenon which here presents itself, and which is known by the name of refraction. 180. In treating of the physiological colours, we have already had occasion to vindicate what were formerly called illusions of sight, as the active energies of the healthy and duly efficient eye, and we are now again invited to consider similar instances confirming the constancy of the laws of vision. 181. Throughout nature, as presented to the senses, everything depends on the relation which things bear to each other, but especially on the relation which man, the most important of these, bears to the rest. Hence the world divides itself into two parts, and the human being as subject stands opposed to the object. Thus the practical man exhausts himself in the accumulation of facts, the thinker in speculation, each being called upon to sustain a conflict which admits of no peace and no decision. 182. But still the main point always is, whether the relations are truly seen. As our senses, if healthy, are the surest witnesses of external relations, so we may be convinced that in all instances where they appear to contradict reality, they lay the greater and surer stress on true relations. Thus a distant object appears to us smaller, and precisely by this means we are aware of distance. We produced coloured appearances on colourless objects, through colourless mediums, and at the same moment our attention was called to the degree of opacity in the medium. 183. Thus the different degrees of opacity in so-called transparent mediums, nay, even other physical and chemical properties belonging to them, are known to our vision by means of refraction, and invite us to make further trials in order to penetrate more completely by physical and chemical means into those secrets which are already opened to our view on one side. 184. Objects seen through mediums more or less transparent do not appear to us in the place which they should occupy according to the laws of perspective. On this fact the dioptrical colours of the second class depend. 185. Those laws of vision which admit of being expressed in mathematical formulae are based on the principle that, as light proceeds in straight lines, it must be possible to draw a straight line from the eye to any given object in order that it be seen. If, therefore, a case arises in which the light arrives to us in a bent or broken line, that we see the object by means of a bent or broken line, we are at once informed that the medium between the eye and the object is denser, or that it has assumed this or that foreign nature. 186. This deviation from the law of right-lined vision is known by the general term of refraction, and although we may take it for granted that our readers are sufficiently acquainted with its effects, yet we will here once more briefly exhibit it in its objective and subjective point of view. 187. Let the sun shine diagonally into an empty cubical vessel, so that the opposite side be illuminated, but not the bottom. Let water be then poured into this vessel, and the direction of the light will be immediately altered, for a part of the bottom is shone upon. At the point where the light enters the thicker medium, it deviates from its rectilinear direction, and appears broken. Hence the phenomenon is called the breaking, Brechung, or refraction. Thus much of the objective experiment. 188. We arrive at the subjective fact in the following mode. Let the eye be substituted for the sun. Let the sight be directed in like manner diagonally over one side, so that the opposite inner side be entirely seen, while no part of the bottom is visible. On pouring in water, the eye will perceive a part of the bottom, and this takes place without our being aware that we do not see in a straight line, for the bottom appears to us raised, and hence we give the term elevation, Hebung, to the subjective phenomenon. Some points which are particularly remarkable with reference to this will be adverted to hereafter. 189. Were we now to express this phenomenon generally, we might here repeat, in conformity with the view lately taken, that the relation of the objects is changed or deranged. 190. But as it is our intention at present to separate the objective from the subjective appearances, we first express the phenomenon in a subjective form and say a derangement or displacement of the object seen or to be seen takes place. 191. But that which is seen without a limiting outline may be thus affected without our perceiving the change. On the other hand, if what we look at has a visible termination, we have an evident indication that a displacement occurs. If, therefore, we wish to ascertain the relation or degree of such a displacement, we must chiefly confine ourselves to the alteration of surfaces with visible boundaries, in other words, to the displacement of circumscribed objects. 192. The general effect may take place through parallel mediums, for every parallel medium displaces the object by bringing it perpendicularly towards the eye. The apparent change of position is, however, more observable through mediums that are not parallel. 193. These latter may be perfectly spherical, or may be employed in the form of convex or concave lenses. We shall make use of all these, as occasion may require, in our experiments. But as they not only displace the object from its position, but alter it in various ways, we shall, in most cases, prefer employing mediums with surfaces not indeed parallel with reference to each other, but still altogether plane, namely prisms. These have a triangle for their base, and may, it is true, be considered as portions of a lens, but they are particularly available for our experiments, inasmuch as they very perceptibly displace the object from its position, without producing a remarkable distortion. 194. And now, in order to conduct our observations with as much exactness as possible, and to avoid all confusion and ambiguity, we confine ourselves at first to subjective experiments, in which, namely, the object is seen by the observer through a refracting medium. As soon as we have treated these in due series, the objective experiments will follow in similar order. End of section 12. Section 13 of Theory of Colours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Gillian Hendry. Theory of Colours by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 13. 12. Refraction without the appearance of colour. 195. Refraction can visibly take place without our perceiving an appearance of colour. To whatever extent a colourless or uniformly coloured surface may be altered as to its position by refraction, no colour consequent upon refraction appears within it, provided it has no outline or boundary. We may convince ourselves of this in various ways. 196. Place a glass cube on any larger surface and look through the glass perpendicularly or obliquely. The unbroken surface opposite the eye appears altogether raised, but no colour exhibits itself. If we look at a pure grey or blue sky, or a uniformly white or coloured wall through a prism, the portion of the surface which the eye thus embraces will be altogether changed as to its position, without our therefore observing the smallest appearance of colour. 13. Conditions of the appearance of colour. 197. Although in the foregoing experiments we have found all unbroken surfaces, large or small, colourless, yet at the outlines or boundaries, where the surface is relieved upon a darker or lighter object, we observe a coloured appearance. 198. Outline as well as surface is necessary to constitute a figure or circumscribed object. We therefore express the leading fact thus: circumscribed objects must be displaced by refraction in order to the exhibition of an appearance of colour. 199. We place before us the simplest object, a light disk on a dark ground, A. A displacement occurs with regard to this object if we apparently extend its outline from the centre by magnifying it. This may be done with any convex glass, and in this case we see a blue edge, B. 200. We can to appearance contract the circumference of the same light disk towards the centre by diminishing the object. The edge will then appear yellow, C. This may be done with a concave glass, which, however, should not be ground thin like common eyeglasses, but must have some substance. In order, however, to make this experiment at once with the convex glass, let a smaller black disk be inserted within the light disk on a black ground. If we magnify the black disk on a white ground with a convex glass, the same result takes place as if we diminished the white disk, for we extend the black outline upon the white, and we thus perceive the yellow edge together with the blue edge, D. 201. These two appearances, the blue and yellow, exhibit themselves in and upon the white. They both assume a reddish hue, in proportion as they mingle with the black. Plate 2. 202. In this short statement we have described the primordial phenomena of all appearance of colour occasioned by refraction. These undoubtedly may be repeated, varied, and rendered more striking, may be combined, complicated, confused, but after all may be still restored to their original simplicity. 203. In examining the process of the experiment just given, we find that in the one case we have to appearance extended the white edge upon the dark surface. In the other we have extended the dark edge upon the white surface, supplanting one by the other, pushing one over the other. We will now endeavour, step by step, to analyse these and similar cases. 204. If we cause the white disk to move in appearance entirely from its place, which can be done effectually by prisms, it will be coloured according to the direction in which it apparently moves, in conformity with the above laws. If we look at the disk A through a prism so that it appear moved to B, the outer edge will appear blue and blue-red, according to the law of the figure B, figure 1. The other edge being yellow and yellow-red, according to the law of the figure C, figure 1. For in the first case the white figure is, as it were, extended over the dark boundary, and in the other case the dark boundary is passed over the white figure. The same happens if the disk is to appearance moved from A to C, from A to D, and so throughout the circle. 205. As it is with the simple effect, so it is with more complicated appearances. If we look through a horizontal prism, AB, at a white disk placed at some distance behind it at E, the disk will be raised to F and coloured according to the above law. If we remove this prism and look through a vertical one, CD, at the same disk, it will appear at H and coloured according to the same law. If we place the two prisms one upon the other, the disk will appear displaced diagonally in conformity with a general law of nature, and will be coloured as before, that is, according to its movement in the direction. 206. If we attentively examine these opposite coloured edges, we find that they only appear in the direction of the apparent change of place. A round figure leaves us in some degree uncertain as to this. A quadrangular figure removes all doubt. 207. The quadrangular figure A, moved in the direction AB or AD, exhibits no colour on the sides which are parallel with the direction in which it moves. On the other hand, if moved in the direction AC, parallel with its diagonal, all the edges of the figure appear coloured. 208. Thus a former position, 203, is here confirmed, namely, to produce colour, an object must be so displaced that the light edges be apparently carried over a dark surface, the dark edges over a light surface, the figure over its boundary, the boundary over the figure. But if the rectilinear boundaries of a figure could be indefinitely extended by refraction, so that figure and background might only pursue their course next, but not over each other. No colour would appear, not even if they were prolonged to infinity. End of section 13.
Section 14 of Theory of Colours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Theory of Colours by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 14. Conditions under which the appearance of colours increases. 209. We have seen in the foregoing experiments that all appearance of colour occasioned by refraction depends on the condition that the boundary or edge be moved in upon the object itself, or the object itself over the ground, that the figure should be, as it were, carried over itself, or over the ground. And we shall now find that, by increased displacement of the object, the appearance of colour exhibits itself in a greater degree. This takes place in subjective experiments, to which, for the present, we confine ourselves under the following conditions. 210. First, if in looking through parallel mediums the eye is directed more obliquely. Secondly, if the surfaces of the medium are no longer parallel, but form a more or less acute angle. Thirdly, owing to the increased proportion of the medium, whether parallel mediums be increased in size, or whether the angle be increased, provided it does not attain a right angle. Fourthly, owing to the distance of the eye armed with a refracting medium for the object to be displaced. Fifthly, owing to a chemical property that may be communicated to the glass, and which may be afterwards increased in effect. 211. The greatest change of place, short of considerable distortion of the object, is produced by means of prisms, and this is the reason why the appearance of colour can be exhibited most powerfully through glasses of this form. Yet we will not, in employing them, suffer ourselves to be dazzled by the splendid appearances they exhibit, but keep the above well-established simple principles calmly in view. 212. The colour which is outside, or foremost, in the apparent change of an object by refraction, is always the broader, and we will henceforth call this a border. The colour that remains next the outline is the narrower, and this we will call an edge. 213. If we move a dark boundary towards a light surface, the yellow broader border is foremost, and the narrower yellow-red edge follows close to the outline. If we move a light boundary towards a dark surface, the broader violet border is foremost, and the narrower blue edge follows. 214. If the object is large, its centre remains uncoloured. Its inner surface is then to be considered as unlimited. It is displaced, but not otherwise altered. But if the object is so narrow that under the above conditions the yellow border can reach the blue edge, the space between the outlines will be entirely covered with colour. If we make this experiment with a white stripe on a black ground, the two extremes will presently meet, and thus produce green. We shall then see the following series of colours: yellow-red, yellow, green, blue, blue-red. 215. If we place a black band or stripe on white paper, the violet border will spread till it meets the yellow-red edge. In this case the intermediate black is effaced, as the intermediate white was in the last experiment, and in its stead a splendid pure red will appear. The series of colours will now be as follows: blue, blue-red, red, yellow-red, yellow. 216. The yellow and blue in the first case can by degrees meet so fully that the two colours blend entirely in green, and the order will then be yellow-red, green, blue-red. In the second case, under similar circumstances, we see only blue, red, yellow. This appearance is best exhibited by refracting the bars of a window when they are relieved on a grey sky. 217. In all this we are never to forget that this appearance is not to be considered as a complete or final state, but always as a progressive, increasing, and in many cases controllable appearance. Thus we find that, by the negation of the above 5 conditions, it gradually decreases and at last disappears altogether. End of section 14.
Section 15 of Theory of Colours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Theory of Colours by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 15. Explanation of the foregoing phenomena. 218. Before we proceed further, it is incumbent on us to explain the first tolerably simple phenomenon, and to show its connection with the principles first laid down, in order that the observer of nature may be enabled clearly to comprehend the more complicated appearances that follow. 219. In the first place, it is necessary to remember that we have to do with circumscribed objects. In the act of seeing, generally, it is the circumscribed visible which chiefly invites our observation, and in the present instance, in speaking of the appearance of colour, as occasioned by refraction, the circumscribed visible, the detached object solely occupies our attention. 220. For our chromatic exhibitions we can, however, divide objects generally into primary and secondary. The expressions of themselves denote what we understand by them, but our meaning will be rendered still more plain by what follows. 221. Primary objects may be considered firstly as original, as images which are impressed on the eye by things before it, and which assure us of their reality. To these the secondary images may be opposed as derived images, which remain in the organ when the object itself is taken away. Those apparent after images, which have been circumstantially treated of in the doctrine of physiological colours. 222. The primary images, again, may be considered as direct images which, like the original impressions, are conveyed immediately from the object to the eye. In contradistinction to these, the secondary images may be considered as indirect, being only conveyed to us as it were, at second hand from a reflecting surface. These are the mirrored or catoptrical images, which in certain cases can also become double images. 223. When, namely, the reflecting body is transparent, and has 2 parallel surfaces, one behind the other. In such a case, an image may be reflected to the eye from both surfaces, and thus arrive double images, inasmuch as the upper image does not quite cover the under one. This may take place in various ways. Let a playing card be held before a mirror. We shall at first see the distinct image of the card, but the edge of the whole card, as well as that of every spot upon it, will be bounded on one side with a border, which is the beginning of the second reflection. This effect varies in different mirrors according to the different thickness of the glass and the accidents of polishing. If a person wearing a white waistcoat with the remaining part of his dress dark stands before certain mirrors, the border appears very distinctly, and in like manner the metal buttons on dark cloth exhibit the double reflection very evidently. 224. The reader who has made himself acquainted with our former descriptions of experiments will the more readily follow the present statement. The window bars reflected by plates of glass appear double, and by increased thickness of the glass, and a due adaptation of the angle of reflection. The 2 reflections may be entirely separated from each other. So a vase full of water, with a plain mirror-like bottom, reflects any object twice, the 2 reflections being more or less separated under the same conditions. In these cases it is to be observed that, where the 2 reflections cover each other, the perfect vivid image is reflected, but where they are separated, they exhibit only weak, transparent, and shadowy images. 225. If we wish to know which is the under and which the upper image, we have only to take a coloured medium, for then a light object reflected from the under surface is of the colour of the medium, while that reflected from the upper surface presents the complemental colour. With dark objects it is the reverse, hence black and white surfaces may be here also conveniently employed. How easily the double images assume and evoke colours will here again be striking. 226. Thirdly, the primary images may be considered as principal images, while the secondary can be, as it were, annexed to those as accessory images. Such an accessory image produces a sort of double form, except that it does not separate itself from the principal object, although it may be said to be always endeavouring to do so. It is with secondary images of this last description that we have to do in prismatic appearances. 227. A surface without a boundary exhibits no appearance of colour when refracted. Whatever is seen must be circumscribed by an outline to produce this effect. In other words, a figure, an object, is required. This object undergoes an apparent change of place by refraction. The change is, however, not complete, not clean, not sharp, but incomplete inasmuch as an accessory image only is produced. 228. In examining every appearance of nature, but especially in examining an important and striking one, we should not remain in one spot. We should not confine ourselves to the insulated fact, nor dwell on it exclusively, but look round through all nature to see where something similar, something that has affinity to it, appears. For it is only by combining analogies that we gradually arrive at a whole which speaks for itself, and requires no further explanation. 229. Thus we here call to mind that in certain cases refraction unquestionably produces double images, as is the case in Iceland spar. Similar double images are also apparent in cases of refraction through large rock crystals, and in other instances, phenomena which have not hitherto been sufficiently observed. 230. But since in the case under consideration the question relates not to double but to accessory images, we refer to a phenomenon already adverted to, but not yet thoroughly investigated. We allude to an earlier experiment in which it appeared that a sort of conflict took place in regard to the retina between a light object and its dark ground, and between a dark object and its light ground. The light object in this case appeared larger, the dark one smaller. 231. By a more exact observation of this phenomenon we may remark that the forms are not sharply distinguished from the ground, but that they appear with a kind of grey, in some degree coloured edge. In short, with an accessory image. If, then, objects seen only with the naked eye produce such effects, what may not take place when a dense medium is interposed? It is not that alone which presents itself to us in obvious operation which produces and suffers effects, but likewise all principles that have a mutual relation only of some sort are efficient accordingly, and indeed often in a very high degree. 232. Thus, when refraction produces its effect on an object that appears in accessory image next to the object itself, the real form thus refracted seems even to linger behind, as if resisting the change of place, but the accessory image seems to advance, and extends itself more or less in the mode already shown. 233. We also remark that in double images the fainter appear only half substantial, having a kind of transparent evanescent character, just as the fainter shades of double shadows must always appear as half shadows. These latter assume colours easily and produce them readily, the former also, and the same takes place in the instance of accessory images, which, it is true, do not altogether quit the real object, but still advance or extend from it as half substantial images, and hence can appear coloured so quickly and so powerfully. 234. That prismatic appearance is in fact an accessory image we may convince ourselves in more than one mode. It corresponds exactly with the form of the object itself, whether the object be bounded by a straight line or a curve, indented or waving. The form of the accessory image corresponds throughout exactly with the form of the object. 235. Again, not only the form but other qualities of the object are communicated to the accessory image. If the object is sharply relieved from its ground, like white on black, the coloured accessory image in like manner appears in its greatest force. It is vivid, distinct, and powerful, but it is most especially powerful when a luminous object is shown on a dark ground, which may be contrived in various ways. 236. But if the object is but faintly distinguished from the ground, like grey objects on black or white, or even on each other, The accessory image is also faint, and, when the original difference of tint or force is slight, becomes hardly discernible. 237. The appearances which are observable when coloured objects are relieved on light, dark, or coloured grounds are, moreover, well worthy of attention. In this case a union takes place between the apparent colour of the accessory image and the real colour of the object. A compound colour is the result, which is either assisted and enhanced by the accordance, or neutralized by the opposition of its ingredients. 238. But the common and general characteristics of both the double and accessory image is semi-transparence. The tendency of a transparent medium to become only half-transparent or merely light-transmitting has been before adverted to. Let the reader assume that he sees within or through such a medium a visionary image, and he will at once pronounce this latter to be a semi-transparent image. 239. Thus the colours produced by refraction may be fitly explained by the doctrine of the semi-transparent mediums. For where dark passes over light, as the border of the semi-transparent accessory image advances, yellow appears, and, on the other hand, where a light outline passes over the dark background, blue appears. 240. The advancing foremost colour is always the broader. Thus the yellow spreads over the light with a broad border, but the yellow-red appears as a narrow stripe and is next the dark, according to the doctrine of augmentation, as an effect of shade. 241. On the opposite side, the condensed blue is next the edge, while the advancing border, spreading as a thinner veil over the black, produces the violet colour, precisely on the principles before explained in treating of semi-transparent mediums, principles which will hereafter be found equally efficient in many other cases. 242. Since an analysis like the present requires to be confirmed by ocular demonstration, we beg every reader to make himself acquainted with the experiments hitherto adduced, not in a superficial manner, but fairly and thoroughly. We have not placed arbitrary signs before him instead of the appearances themselves. No modes of expression are here proposed for his adoption, which may be repeated for ever without the exercise of thought and without leading any one to think. But we invite him to examine intelligible appearances which must be present to the eye and mind, in order to enable him clearly to trace these appearances to their origin, and to explain them to himself and to others. End of section 15.
Section 16 of Theory of Colours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Theory of Colours by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 16. Decrease of the appearance of colour. 243. We need only take the 5 conditions under which the appearance of colour increases in the contrary order to produce the contrary or decreasing state. It may be as well, however, briefly to describe and review the corresponding modifications which are present to the eye. 244. At the highest point of complete junction of the opposite edges, the colours appear as follows: yellow-red, blue, green, red, blue-red, yellow. 245. Where the junction is less complete, the appearance is as follows: yellow-red, blue, yellow, blue-red, green, red, blue, yellow-red, blue-red, yellow. Here, therefore, the surface still appears completely coloured, but neither series is to be considered as an elementary series, always developing itself in the same manner and in the same degrees. On the contrary, they can and should be resolved into their elements, and in doing this we become better acquainted with their nature and character. 246. These elements then are yellow, red, blue, yellow, blue, red, white, black, blue, yellow, red, blue, red, yellow. Here the surface itself, the original object, which has been hitherto completely covered, and, as it were, lost, again appears in the centre of the colours, asserts its right, and enables us fully to recognise the secondary nature of the accessory images which exhibit themselves as edges and borders. 247. We can make these edges and borders as narrow as we please, nay, we can still have refraction in reserve after having done away with all appearance of colour at the boundary of the object. Having now sufficiently investigated the exhibition of colour in this phenomenon, we repeat that we cannot admit it to be an elementary phenomenon. On the contrary, we have traced it to an antecedent and a simpler one. We have derived it, in connection with the theory of secondary images, from the primordial phenomenon of light and darkness, as affected or acted upon by semi-transparent mediums. Thus prepared, we proceed to describe the appearances which refraction produces on grey and coloured objects, and this will complete the section of subjective phenomena. Section 17. Grey objects displaced by refraction. 248. Hitherto we have confined our attention to black and white objects relieved on respectively opposite grounds, as seen through the prism, because the coloured edges and borders are most clearly displayed in such cases. We now repeat these experiments with grey objects, and again find similar results. 249. As we called black the equivalent of darkness and white the representative of light, so we now venture to say that grey represents half shadow, which partakes more or less of light and darkness, and thus stands between the two. We invite the reader to call to mind the following facts as bearing on our present view. 250. Grey objects appear lighter on a black than on a white ground. They appear as a light on a black ground, and larger, as a dark on a white ground, and smaller. 251. The darker the grey, the more it appears as a faint light on black, as a strong dark on white, and vice versa. Hence the accessory images of dark grey on black are faint, on white strong. So the accessory images of light grey on white are faint, on black strong. 252. Grey on black, seen through the prism, will exhibit the same appearances as white on black. The edges are coloured according to the same law, only the borders appear fainter. If we relieve grey on white, we have the same edges and borders which would be produced if we saw black on white through the prism. 253. Various shades of grey placed next each other in gradation will exhibit at their edges either blue and violet only, or red and yellow only, according as the darker grey is placed over or under. 254. A series of such shades of grey placed horizontally next each other will be coloured conformably to the same according as the whole series is relieved on a black or white ground above or below. 255. The observer may see the phenomena exhibited by the prism at one glance, by enlarging the plate intending to illustrate this section. 256. It is of great importance duly to examine and consider another experiment in which a grey object is placed partly on a black and partly on a white surface, so that the line of division passes vertically through the object. 257. The colours will appear on this grey object in conformity with the usual law, but according to the opposite relation of the light to the dark, and will be contrasted in a line. For as the grey is as a light to the black, so it exhibits the red and yellow above the blue and violet below. Again, as the grey is as a dark to the white, the blue and violet appear above the red and yellow below. This experiment will be found of great importance with reference to the next chapter. End of section 16.
Section 17 of Theory of Colours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Gillian Hendry. Theory of Colours by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 17. 18. Coloured objects displaced by refraction. 258. An unlimited coloured surface exhibits no prismatic colour in addition to its own hue, thus not at all differing from a black, white, or grey surface. To produce the appearance of colour, light and dark boundaries must act on it, either accidentally or by contrivance. Hence experiments and observations on coloured surfaces, as seen through the prism, can only be made when such surfaces are separated by an outline from another differently tinted surface, in short, when circumscribed objects are coloured. 259. All colours, whatever they may be, correspond so far with grey that they appear darker than white and lighter than black. This shade-like quality of colour, skieron, has been already alluded to at 69, and will become more and more evident. If then we begin by placing coloured objects on black and white surfaces, and examine them through the prism, we shall again have all that we have seen exhibited with grey surfaces. 260. If we displace a coloured object by refraction, there appears, as in the case of colourless objects and according to the same laws, an accessory image. This accessory image retains, as far as colour is concerned, its usual nature, and acts on one side as a blue and blue-red, on the opposite side as a yellow and yellow-red. Hence the apparent colour of the edge and border will be either homogeneous with the real colour of the object, or not so. In the first case the apparent image identifies itself with the real one, and appears to increase it, while in the second case the real image may be vitiated, rendered indistinct, and reduced in size by the apparent image. We proceed to review the cases in which these effects are most strikingly exhibited. 261. If we take a coloured drawing enlarged from the plate, which illustrates this experiment, and examine the red and blue squares placed next to each other on a black ground, through the prism as usual, we shall find that as both colours are lighter than the ground, similarly coloured edges and borders will appear above and below, at the outlines of both, only they will not appear equally distinct to the eye. 262. Red is proportionally much lighter on black than blue is. The colours of the edges will therefore appear stronger on the red than on the blue, which here acts as a dark grey, but little different from black. 263. The extreme red edge will identify itself with the vermilion colour of the square, which will thus appear a little elongated in this direction, while the yellow border immediately underneath it only gives the red surface a more brilliant appearance, and is not distinguished without attentive observation. 264. On the other hand, the red edge and yellow border are heterogeneous with the blue square. A dull red appears at the edge, and a dull green mingles with the figure, and thus the blue square seems, at a hasty glance, to be comparatively diminished on this side. 265. At the lower outline of the two squares a blue edge and a violet border will appear, and will produce the contrary effect, for the blue edge, which is heterogeneous with the warm red surface, will vitiate it, and produce a neutral colour, so that the red on this side appears comparatively reduced and driven upwards, and the violet border on the black is scarcely perceptible. 266. On the other hand, the blue apparent edge will identify itself with the blue square, and not only not reduce, but extend it. The blue edge and even the violet border next it have the apparent effect of increasing the surface and elongating it in that direction. 267. The effect of homogeneous and heterogeneous edges, as I have now minutely described it, is so powerful and singular that the two squares at the first glance seem pushed out of their relative horizontal position and moved in opposite directions, the red upwards, the blue downwards. But no one who is accustomed to observe experiments in a certain succession, and respectively to connect and trace them, will suffer himself to be deceived by such an unreal effect. 268. A just impression with regard to this important phenomenon will, however, much depend on some nice and even troublesome conditions, which are necessary to produce the illusion in question. Paper should be tinged with vermilion or the best minium for the red square, and with deep indigo for the blue square. The blue and red prismatic edges will then unite imperceptibly with the real surfaces where they are respectively homogeneous. Where they are not, they vitiate the colours of the squares without producing a very distinct middle tint. The real red should not incline too much to yellow, otherwise the apparent deep red edge above will be too distinct. At the same time it should be somewhat yellow, otherwise the transition to the yellow border will be too observable. The blue must not be light, otherwise the red edge will be visible and the yellow border will produce a too decided green, while the violet border underneath would not give us the impression of being part of an elongated light blue square. 269. All this will be treated more circumstantially hereafter, when we speak of the apparatus intended to facilitate the experiments connected with this part of our subject. Every inquirer should prepare the figures himself in order fairly to exhibit this specimen of ocular deception, and at the same time to convince himself that the coloured edges, even in this case, cannot escape accurate examination. 270. Meanwhile, various other combinations, as exhibited in the plate, are fully calculated to remove all doubt on this point in the mind of every attentive observer. 271. If, for instance, we look at a white square next the blue one on a black ground, the prismatic hues of the opposite edges of the white, which here occupies the place of the red in the former experiment, will exhibit themselves in their utmost force. The red edge extends itself above the level of the blue almost in a greater degree than was the case with the red square itself in the former experiment. The lower blue edge again is visible in its full force next the white, while on the other hand it cannot be distinguished next the blue square. The violet border underneath is also much more apparent on the white than on the blue. 272. If the observer now compares these double squares, carefully prepared and arranged one above the other, the red with the white, the two blue squares together, the blue with the red, the blue with the white, he will clearly perceive the relations of these surfaces to their coloured edges and borders. 273. The edges and their relations to the coloured surfaces appear still more striking if we look at the coloured squares and a black square on a white ground, for in this case the illusion before mentioned ceases altogether, and the effect of the edges is as visible as in any case that has come under our observation. Let the blue and red squares be first examined through the prism. In both, the blue edge now appears above. This edge, homogeneous with the blue surface, unites with it and appears to extend it upwards, only the blue edge, owing to its lightness, is somewhat too distinct in its upper portion. The violet border underneath it is also sufficiently evident on the blue. The apparent blue edge is, on the other hand, heterogeneous with the red square. It is neutralized by contrast and is scarcely visible. Meanwhile, the violet border, uniting with the real red, produces a hue resembling that of the peach blossom. 274. If thus, owing to the above causes, the upper outlines of these squares do not appear level with each other, the correspondence of the under outlines is the more observable, for since both colours, the red and the blue, are darks compared with the white, as in the former case they were light compared with the black, the red edge with its yellow border appears very distinctly under both. It exhibits itself under the warm red surface in its full force, and under the dark blue nearly as it appears under the black, as may be seen if we compare the edges and borders of the figures placed one above the other on the white ground. 275. In order to present these experiments with the greatest variety and perspicuity, squares of various colours are so arranged that the boundary of the black and white passes through them vertically. According to the laws now known to us, especially in their application to coloured objects, we shall find the squares as usual doubly coloured at each edge. Each square will appear to be split in two, and to be elongated upwards or downwards. We may here call to mind the experiment with the grey figure, seen in like manner on the line of division between black and white. 257. 276. A phenomenon was before exhibited, even to illusion, in the instance of a red and blue square on a black ground. In the present experiment, the elongation upwards and downwards of two differently coloured figures is apparent in the two halves of one and the same figure of one and the same colour. Thus we are still referred to the coloured edges and borders, and to the effects of their homogeneous and heterogeneous relations with respect to the real colours of the objects. 277. I leave it to observers themselves to compare the various gradations of coloured squares, placed half on black, half on white, only inviting their attention to the apparent alteration which takes place in contrary directions. For red and yellow appear elongated upwards if on a black ground, downwards if on a white. Blue, downwards if on a black ground, upwards if on a white. All which, however, is quite in accordance with the diffusely detailed examples above given. 278. Let the observer now turn the figures so that the before-mentioned squares placed on the line of division between black and white may be in a horizontal series, the black above, the white underneath. On looking at these squares through the prism, he will observe that the red square gains by the addition of two red edges. On more accurate examination, he will observe the yellow border on the red figure, and the lower yellow border upon the white will be perfectly apparent. 279. The upper red edge on the blue square is on the other hand hardly visible. The yellow border next it produces a dull green by mingling with the figure. The lower red edge and the yellow border are displayed in lively colours. 280. After observing that the red figure in these cases appears to gain by an addition on both sides, while the dark blue on one side at least loses something, we shall see the contrary effect produced by turning the same figures upside down, so that the white ground be above, the black below. 281. For as the homogeneous edges and borders now appear above and below the blue square, this appears elongated, and a portion of the surface itself seems even more brilliantly coloured. It is only by attentive observation that we can distinguish the edges and borders from the colour of the figure itself. 282. The yellow and red squares, on the other hand, are comparatively reduced by the heterogeneous edges in this position of the figures, and their colours are, to a certain extent, vitiated. The blue edge in both is almost invisible. The violet border appears as a beautiful peach blossom hue on the red, as a very pale colour of the same kind on the yellow. Both the lower edges are green, dull on the red, vivid on the yellow. The violet border is but faintly perceptible under the red, but is more apparent under the yellow. 283. Every inquirer should make it a point to be thoroughly acquainted with all the appearances here adduced, and not consider it irksome to follow out a single phenomenon through so many modifying circumstances. These experiments, it is true, may be multiplied to infinity by differently coloured figures, upon and between differently coloured grounds. Under all such circumstances, however, it will be evident to every attentive observer that coloured squares only appear relatively altered, or elongated, or reduced by the prism, because an addition of homogeneous or heterogeneous edges produces an illusion. The inquirer will now be enabled to do away with this illusion if he has the patience to go through the experiments one after the other, always comparing the effects together, and satisfying himself of their correspondence. Experiments with coloured objects might have been contrived in various ways. Why they have been exhibited precisely in the above mode, and with so much minuteness, will be seen hereafter. The phenomena, although formerly not unknown, were much misunderstood, and it was necessary to investigate them thoroughly to render some portions of our intended historical view clearer. 284. In conclusion, we will mention a contrivance by means of which our scientific readers may be enabled to see these appearances distinctly at one view, and even in their greatest splendour. cut in a piece of pasteboard 5 perfectly similar square openings of about an inch next each other, exactly in a horizontal line. Behind these openings place 5 coloured glasses in the natural order orange, yellow, green, blue, violet. Let the series thus adjusted be fastened in an opening of the camera obscura, so that the bright sky may be seen through the squares, or that the sun may shine on them. They will thus appear very powerfully coloured. Let the spectator now examine them through the prism, and observe the appearances, already familiar by the foregoing experiments, with coloured objects, namely, the partly assisting, partly neutralizing effects of the edges and borders, and the consequent apparent elongation or reduction of the coloured squares with reference to the horizontal line. The results witnessed by the observer in this case entirely correspond with those in the cases before analysed. We do not therefore go through them again in detail, especially as we shall find frequent occasions hereafter to return to the subject. Footnote: the earnestness and pertinacity with which Goethe insisted that the different colours are not subject to different degrees of refrangibility are at least calculated to prove that he was himself convinced on the subject, and however extraordinary it may seem, his conviction appears to have been the result of infinite experiments and the fullest ocular evidence. He returns to the question in the controversial division of his work, in the historical part, and again in the description of the plates. In the first he endeavours to show that Newton's experiment with the blue and red paper depends entirely on the colours being so contrived as to appear elongated or curtailed by the prismatic borders. If, he says, we take a light blue instead of a dark one, the illusion in the latter case is at once evident. According to the Newtonian theory, the yellow-red, red, is the least refrangible colour, the violet the most refrangible. Why then does Newton place a blue paper instead of a violet next the red? If the fact were as he states it, the difference in the refrangibility of the yellow-red and violet would be greater than in the case of the yellow-red and blue. But here comes in the circumstance that a violet paper conceals the prismatic borders less than a dark blue paper, as every observer may now easily convince himself, and so on. Polemischer Teil, paragraph 45. De Saguier, in repeating the experiment, confessed that if the ground of the colours was not black, the effect did not take place so well. Goethe adds, not only not so well, but not at all. Historischer Teil, page 459. Lucas of Lüttich, one of Newton's first opponents, denied that two differently coloured silks are different in distinctness when seen in the microscope. Another experiment proposed by him, to show the unsoundness of the doctrine of various refrangibility, was the following: that a tin plate painted with the prismatic colours in stripes be placed in an empty cubical vessel, so that from the spectator's point of view the colours may be just hidden by the rim. On pouring water into this vessel, all the colours become visible in the same degree, whereas, it was contended, if the Newtonian doctrine were true, some colours would be apparent before others. Historischer Teil, page 434. Such are the arguments and experiments adduced by Goethe on this subject. They have all probably been answered. In his analysis of Newton's celebrated Experimentum Crucis, he shows again that by reversing the prismatic colours, refracting a dark instead of a light object, the colours that are the most refrangible in Newton's experiment become the least so, and vice versa. Without reference to this objection, it is now admitted that the difference of colour is not a test of difference of refrangibility, and the conclusion deduced by Newton is no longer admissible as a general truth, that to the same degree of refrangibility ever belongs the same colour, and to the same colour ever belongs the same degree of refrangibility. Brewster's Optics, page 72. End of footnote. End of section 17.
Section 18 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 18. Part 19. Achromatism and Hyperchromatism. 285. Formerly, when much that is regular and constant in nature was considered as mere aberration and accident, the colours arising from refraction were but little attended to, and were looked upon as an appearance attributable to particular local circumstances. 286. But after it had been assumed that this appearance of colour accompanies refraction at all times, it was natural that it should be considered as intimately and exclusively connected with that phenomenon, the belief obtaining that the measure of the coloured appearance was in proportion to the measure of the refraction, and that they must advance pari passu with each other. 287. If, again, philosophers ascribe the phenomenon of a stronger or weaker refraction, not indeed wholly, but in some degree, to the different density of the medium, as pure atmospheric air, air charged with vapours, water, glass, according to their increasing density, increase the so-called refraction, or displacement of the object, so they could hardly doubt that the appearance of colour must increase in the same proportion, and hence took it for granted, in combining different mediums which were to counteract refraction, that as long as refraction existed, the appearance of colour must take place, and that as soon as the colour disappeared, the refraction also must cease. 288. Afterwards it was, however, discovered that this relation which was assumed to correspond was in fact dissimilar, that two mediums can refract an object with equal power, and yet produce very dissimilar coloured borders. 289. It was found that in addition to the physical principle to which refraction was ascribed, a chemical one was also to be taken into the account. We propose to pursue this subject hereafter in the chemical division of our inquiry, and we shall have to describe the particulars of this important discovery in our history of the doctrine of colours. What follows may suffice for the present. 290. In mediums of similar or nearly similar refracting power, we find the remarkable circumstance that a greater and lesser appearance of colour can be produced by a chemical treatment. The greater effect is owing, namely, to acids, the lesser to alkalis. If metallic oxides are introduced into a common mass of glass, the coloured appearance through such glasses becomes greatly increased without any perceptible change of refracting power. That the lesser effect, again, is produced by alkalis may be easily supposed. 291. Those kinds of glass which were first employed after the discovery are called flint and crown glass. The first produces the stronger, the second the fainter appearance of colour. 292. We shall make use of both these denominations as technical terms in our present statement, and assume that the refractive power of both is the same, but that flint glass produces the coloured appearance more strongly by 1/3 than the crown glass. The diagram, Plate 3, Fig. 2, may serve in illustration. 293. A black surface is here divided into compartments for more convenient demonstration. Let the spectator imagine 5 white squares between the parallel lines A, B, and C, D. The square number 1 is presented to the naked eye unmoved from its place. 294. But let the square number 2, seen through a crown glass prism, G, be supposed to be displaced by refraction 3 compartments, exhibiting the coloured borders to a certain extent. Again, let the square number 3, seen through a flint glass prism, H, in like manner be moved downwards 3 compartments, when it will exhibit the coloured borders by about 1/3 wider than number 2. 295. Again, let us suppose that the square number 4 has, like number 2, been moved downwards 3 compartments by a prism of crown glass, and that then, by an oppositely placed prism H of flint glass, it has been again raised to its former situation where it now stands. 296. Here, it is true, the refraction is done away with by the opposition of the two, but as the prism H, in displacing the square by refraction through 3 compartments, produces coloured borders wider by 1/3 than those produced by the prism G, so, notwithstanding the refraction is neutralized, there must be an excess of coloured border remaining. The position of this colour, as usual, depends on the direction of the apparent motion, 204, communicated to the square by the prism H, and, consequently, it is the reverse of the appearance in the two squares 2 and 3, which have been moved in an opposite direction. This excess of color we have called hyperchromatism, and from this the achromatic state may be immediately arrived at. 297. For assuming that it was the square number 5 which was removed 3 compartments from its first supposed place, like number 2, by a prism of crown glass G, it would only be necessary to reduce the angle of a prism of flint glass H, and to connect it, reversed, to the prism G, in order to raise the square number 5 2 degrees, or compartments, by which means the hyperchromatism of the first case would cease, the figure would not quite return to its first position, and yet be already colorless. The prolonged lines of the united prisms under number 5 show that a single complete prism remains. Again, we have only to suppose the lines curved, and an object glass presents itself. Such is the principle of the achromatic telescopes. 298. For these experiments, a small prism, composed of 3 different prisms as prepared in England, is extremely well adapted. It is to be hoped our own opticians will in future enable every friend of science to provide himself with this necessary instrument. Part 20. Advantages of subjective experiments. Transition to the objective. 299. We have presented the appearances of color as exhibited by refraction, first by means of subjective experiments, and we have so far arrived at a definite result that we have been enabled to deduce the phenomena in question from the doctrine of semi-transparent mediums and double images. 300. In statements which have reference to nature, everything depends on ocular inspection, and these experiments are the more satisfactory as they may be easily and conveniently made. Every amateur can procure his apparatus without much trouble or cost, and if he is a tolerable adept in pasteboard contrivances, he may even prepare a great part of his machinery himself. A few plain surfaces on which black, white, gray, and colored objects may be exhibited alternately on a light and dark background, are all that is necessary. The spectator fixes them before him, examines the appearances at the edge of the figures conveniently, and as long as he pleases. He retires to a greater distance, again approaches, and accurately observes the progressive states of the phenomena. 301. Besides this, the appearances may be observed with sufficient exactness through small prisms, which need not be of the purest glass. The other desirable requisites in these glass instruments will, however, be pointed out in the section which treats of the apparatus. Footnote. This description of the apparatus was never given. End footnote. 302. A great advantage in these experiments again is that they can be made at any hour of the day in any room, whatever aspect it may have. We have no need to wait for sunshine, which in general is not very propitious to northern observers. Objective experiments. 303. The objective experiments, on the contrary, necessarily require the sunlight which, even when it is to be had, may not always have the most desirable relation with the apparatus placed opposite to it. Sometimes the sun is too high, sometimes too low, and withal only a short time in the meridian of the best situated room. It changes its direction during the observation. The observer is forced to alter his own position, and that of his apparatus, in consequence of which the experiments in many cases become uncertain. If the sun shines through the prism, it exhibits all inequalities, lines, and bubbles in the glass, and thus the appearance is rendered confused, dim, and discolored. 304. Yet both kinds of experiments must be investigated with equal accuracy. They appear to be opposed to each other, and yet are always parallel. What one order of experiments exhibits, the other exhibits likewise, and yet each has its peculiar capabilities, by means of which certain effects of nature are made known to us in more than one way. 305. In the next place, there are important phenomena which may be exhibited by the union of subjective and objective experiments. The latter experiments again have this advantage, that we can in most cases represent them by diagrams, and present to view the component relations of the phenomena. In proceeding, therefore, to describe the objective experiments, we shall so arrange them that they may always correspond with the analogous subjective examples. For this reason, too, we annex to the number of each paragraph the number of the former corresponding one. But we set out by observing generally that the reader must consult the plates, that the scientific investigator must be familiar with the apparatus, in order that the twin phenomena in one mode or the other may be placed before them. End of section 18. Recording by Philip Gould. Section 19 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 21. Refraction without the appearance of color. 306, 195, 196. That refraction may exhibit its effects without producing an appearance of color is not to be demonstrated so perfectly in objective as in subjective experiments. We have, it is true, unlimited spaces which we can look at through the prism, and thus convince ourselves that no color appears where there is no boundary. But we have no unlimited source of light which we can cause to act through the prism. Our light comes to us from circumscribed bodies, and the sun, which chiefly produces our prismatic appearances, is itself only a small circumscribed luminous object. 307. We may, however, consider every larger opening through which the sun shines, every larger medium through which the sunlight is transmitted and made to deviate from its course, as so far unlimited that we can confine our attention to the center of the surface without considering its boundaries. 308. 197. If we place a large water prism in the sun, a large bright space is refracted upwards by it on the plane intended to receive the image, and the middle of this illumined space will be colorless. The same effect may be produced if we make the experiment with glass prisms having angles of few degrees. The appearance may be produced even through glass prisms whose refracting angle is 60 degrees, provided we place the recipient surface near enough. Section 22. Conditions of the appearance of color. 309, 198. Although then the illumined space before mentioned appears indeed refracted and moved from its place, but not colored, yet on the horizontal edges of this space we observe a colored appearance. That here again the color is solely owing to the displacement of a circumscribed object may require to be more fully proved. The luminous body which here acts is circumscribed. The sun, while it shines and diffuses light, is still an insulated object. However small the opening in the lid of a camera obscura be made, still the whole image of the sun will penetrate it. The light which streams from all parts of the sun's disk will cross itself in the smallest opening, and form the angle which corresponds with the sun's apparent diameter. On the outside we have a cone narrowing to the orifice. Within, this apex spreads again, producing on an opposite surface a round image, which still increases in size in proportion to the distance of the recipient surface from the apex. This image, together with all other objects of the external landscape, appears reversed on the white surface in question in a dark room. 310. How little, therefore, we have here to do with single sun rays, bundles or fasces of rays, cylinders of rays, pencils, or whatever else of the kind may be imagined, is strikingly evident. For the convenience of certain diagrams, the sunlight may be assumed to arrive in parallel lines. But it is known that this is only a fiction quite allowable where the difference between the assumption and the true appearance is unimportant. But we should take care not to suffer such a postulate to be equivalent to a fact, and proceed to further operations on such a fictitious basis. 311. Let the aperture in the window shutter be now enlarged at pleasure. Let it be made round or square. Nay, let the whole shutter be opened, and let the sun shine into the room through the whole window. The space which the sun illumines will always be larger according to the angle which its diameter makes, and thus even the whole space illumined by the sun through the largest window is only the image of the sun plus the size of the opening. We shall hereafter have occasion to return to this. 312, 199. If we transmit the image of the sun through convex glasses, we contract it towards the focus. In this case, according to the laws before explained, a yellow border and a yellow-red edge must appear when the spectrum is thrown on white paper. But as this experiment is dazzling and inconvenient, it may be made more agreeably with the image of the full moon. On contracting this orb by means of a convex glass, the colored edge appears in the greatest splendor, for the moon transmits a mitigated light in the first instance, and can thus the more readily produce color which to a certain extent accompanies the subduing of light. At the same time, the eye of the observer is only gently and agreeably excited. 313 (200). If we transmit a luminous image through concave glasses, it is dilated. Here the image appears edged with blue. 314. The two opposite appearances may be produced by a convex glass simultaneously or in succession. Simultaneously by fastening an opaque disc in the center of the convex glass, and then transmitting the sun's image. In this case the luminous image and the black disc within it are both contracted, and, consequently, the opposite colors must appear. Again, we can present this contrast in succession by first contracting the luminous image towards the focus, and then suffering it to expand again beyond the focus, when it will immediately exhibit a blue edge. 315 (201). Here, too, what was observed in the subjective experiments is again to be remarked, namely, that blue and yellow appear in and upon the white, and that both assume a reddish appearance in proportion as they mingle with the black. 316 (202 203). These elementary phenomena occur in all subsequent objective experiments, as they constituted the groundwork of the subjective ones. The process, too, which takes place is the same. A light boundary is carried over a dark surface. A dark surface is carried over a light boundary. The edges must advance, and, as it were, push over each other in these experiments as in the former ones. 317 (204). If we admit the sun's image through a larger or smaller opening into the dark room, if we transmit it through a prism so placed that its refracting angle as usual is underneath, the luminous image, instead of proceeding in a straight line to the floor, is refracted upwards on a vertical surface placed to receive it. This is the moment to take notice of the opposite modes in which the subjective and objective refractions of the object appear. 318. If we look through a prism held with its refracting angle underneath, at an object above us, the object is moved downwards, whereas a luminous image refracted through the same prism is moved upwards. This, which we here merely mention as a matter of fact for the sake of brevity, is easily explained by the laws of refraction and elevation. 319. The luminous object being moved from its place in this manner, the colored borders appear in the order and according to the laws before explained. The violet border is always foremost, and thus in objective cases proceeds upwards, in subjective cases downwards. 320 (205). The observer may convince himself in like manner of the mode in which the appearance of color takes place in the diagonal direction when the displacement is effected by means of two prisms, as has been plainly enough shown in the subjective example. For this experiment, however, prisms should be procured of few degrees, say about 15. 321 (206 207). That the coloring of the image takes place here too, according to the direction in which it moves, will be apparent if we make a square opening of moderate size in a shutter, and cause the luminous image to pass through a water prism. The spectrum being moved first in the horizontal and vertical directions, then diagonally, the colored edges will change their position accordingly. 322 (208). Whence it is again evident that to produce color the boundaries must be carried over each other, not merely moved side by side. End of section 19. Recording by Philip Gould.